Good morning, all of you, and welcome back to the class. So let's continue our topic of machines. And if you remember, we did till we did discussion regarding efficiency, mechanical advantage, and velocity ratio. So today we are going to find out relationship between efficiency, mechanical advantage, and velocity ratio. Children, if we suppose a machine, let it overcomes a load L and it moves by a distance dl on application of effort E in time t, and let d is the distance moved on of effort, right? So as we know that, as I told you in my previous lecture, that efficiency is always given by ratio of work output to work input, right? So here, because we are talking about how much work has been done, so we are talking about only the terminology work done. Here we are not discussing power or energy, right? So as we know that work input is given by effort and displacement of effort, that is E into dE, and same way work output is given by L into dL, that is load into displacement of load. And as we know, efficiency is given by work output to work input. So if we substitute the values of work output and work input, we get, if you can see on the screen, L upon E into dl upon de, or I can say L into dl upon E into de, right? So if we shift the term dl in the denominator, you will see that we get a ratio of de upon dl. And from our previous lecture, if you remember, dE upon dL is actually velocity ratio. So now if we rearrange the terms, we get mechanical advantage is equal to efficiency into velocity ratio. Fine. So what is the difference for ideal machine and practical machine? For ideal machine and practical machine, the work input is equal to work output and mechanical advantage is equal to velocity ratio. And for practical machine, work input is more than work output. I mean, the input given on the load is more, and the output that we are getting is very less as compared to the input. What is the reason behind that? It is because most of the energy while transformation, there is loss of energy, right? When work is being done, a part of the energy, it gets wasted in the form of energy, right? And that energy, that wastage may be due to the frictional force existing, and it may be lost in the form of heat or radiation, and so on, right? So for practical machine, we have work input more than work output, and your velocity ratio is greater than mechanical advantage. So now children, we are going to start with the next section of the chapter, that is levers. So levers are the simplest kinds of machines that we deal in our daily life, right? And what is a lever? Lever is a rigid, straight or bent bar which is capable of turning about a fixed axis. And you must have seen in our daily life, we have seen so many examples of levers, right? We have you must have seen seesaw, you must have seen beam balance, there is a nutcracker, maybe sugar tongs, and so many examples are there. So we'll be discussing about all these examples in detail one by one. Okay, so levers, they have been classified into three classes. They have been classified class 1 lever, class 2 lever, and class 3 lever. So this diversification of this bifurcation or division of levers into three classes, on what parameter that has been done? It is done on the placement or the position of the fulcrum. So you simply need to remember the terminology FLE, F-L-E. So what it symbolizes? It simply tells you F stands for it's class 1 lever. That fulcrum is in center for class 1. L is in center for class 2 lever. And E is in center for class 3 lever. Now if you are viewing the slide, you can see on the screen that in class 1 lever, fulcrum is in the center. right? So now it depends upon the position of the fulcrum, whether it is in the center or towards effort or towards low. Depending upon that, we can actually there is depending upon the position of fulcrum, we can have the different functions of machines performed by only class 1 lever. Like, if you remember, we did the different functions of machines. You remember we discussed about force multiplier, gain in speed, change of direction, right? So all this, so all these things are available in class 1. All these functions can be performed by class 1 lever. And how come it's possible? Only on the change of the placement of fulcrum, we can have the different functions of the machines. Now, the distance between fulcrum and effort is known as effort arm, and distance between fulcrum and load is known as load arm. So if you see from the figure, if fulcrum is in the center, then effort arm will be equal to load arm. And if fulcrum is being shifted towards load, then effort arm will become more than load arm. And if effort is shifted towards your effort, then load arm will become more than effort arm. And similarly, if you can see for class 2 lever in the picture, effort arm is more than load arm because effort is in the extreme end, isn't it? Load is in the center and then is the effort. So here load arm is less than effort arm in class 2. And in class 3 we have load arm is more than effort arm. So depending upon that, now we are going to start with the principle of lever. As we discussed, lever is a machine. So on what principle it is working? Children, you remember we did principle of moments in our first chapter, that turning effect, torque and all those things. Yes, I think you remember. So principle of lever is based on principle of moments. So you remember principle of moments? Yes, it was in equilibrium, sum of clockwise moments is equal to sum of anti-clockwise moments. And same way, for principle of lever, we have clockwise moment of load about the fulcrum is equal to anti-clockwise moment of effort about the fulcrum. That is, load into load arm is equal to effort into effort arm. So if you arrange the terms, we get L upon E is equal to EA upon LA. And if you remember, this is according to the definition of mechanical advantage. Mechanical advantage is given by ratio of load to effort. So if we substitute the values, we get mechanical advantage is equal to effort upon arm upon load arm. So if you see from class 1 levers, the figure that has been given to you, the pictorial representation. Here if you see, we can have both, we can have all the three functions. That mechanical advantage will be, it can be greater than 1, less than 1 and equal to 1. That is, for class 1 lever, class 1 lever machines, they may act as a force multiplier, they may help you to gain speed and they may help you to change the direction as well, convenient in a convenient direction, right? And class 2 lever, here mechanical advantage is greater than 1. That is, class 2 levers, they only, I'm using the word only, it only acts as a force multiplier, whereas for class 3, it is mechanical advantage is less than 1. That is, it helps you to gain speed, right? So from the three classes of levers, you must have seen, you might be having a confusion that class 1 lever is performing all the functions. I mean to say, it is mechanical advantage is greater than 1, less than 1 and equal to 1. And the same functions are being performed by class 2 and class 3 levers. Then how come class 2, class 3, the two classes, they are different from class 1? The basic difference is in the position of the fulcrum. Suppose you get two diagrams where you have and both the diagrams they depict that both are acting as a force multiplier or both are acting as that machine is helping you to gain speed, right? So how to differentiate which one is class 1 and which one is class 2? Because the figure may be telling you that the two are performing the same functions, right? So how to judge it? the way is to find out the position of the fulcrum. If the position of the fulcrum is in the center of effort and load, right, then that will act as class 1. And if the position of the fulcrum is at one extreme, I mean to say load is in the center, then that will act as class 2 lever. So I hope so. You must be clear about the levers now, right? So now we'll be working on the different examples and few application based questions and the numericals based on the concept of levers and the classes of levers.